Good morning, students. Then let's start our lesson. So I'm recording our lesson. I'll put it on our Telegram channel after finishing the lesson. Today we are going to solve problems from sample test published in Didactica. So I looked at the file. It consists of 3 parts. The first part is mechanics, problems on mechanics. And second type of questions are considered about liquids. And the third type of questions concern thermodynamics. Today we are going to deal with mechanics. Today we solve questions from mechanics, and I have sorted all the questions in the order of usual physics teaching. So we start with number 14. A steel ball is released from a height h, falls to the ground and bounces back. Neglecting the friction with air, the height it will attain after the rebound. So this question concerns kinematics, free-falling motion, and if you neglect the air resistance, air friction, then the height after bouncing back will be equal to the initial height if the collision is perfectly elastic. That means perfectly elastic means body doesn't lose its energy during the impact. That's why, according to the conservation of energy, what initial energy has the body, then after collision it will have the same total energy, and again comes back to the original height because of it has the same energy. So according to the energy conservation law, so initial energy should be equal to final energy. So initially it has no potential energy and no kinetic energy, only potential energy. So initial energy is initial potential energy, potential initial. And final energy is also potential energy, potential final. And if you write potential energy as mgh initial equal to mgh final. And canceling out mg gives you h initial equals h final. So that's why final height will be equal to initial height. The answer is 1. So always in these all questions, the correct answer is the first answer, as mentioned at the end of the file. Any questions here? I think it's easiest question. No questions here. Next one is question number 6. A periodic motion is described by the equation the second derivative from x, the coordinate, with respect to time is equal to minus ax, where a is 100 second power minus 2. What is the period t of this motion? So this is this is called simple harmonic motion. This is also kinematics. So the topic is simple harmonic motion. You can see the video lectures of simple harmonic motion, or you can look at the textbook by Alessandro Bettini, and you can read about this simple harmonic motion. I will just solve this question. This is equation of simple harmonic motion. Usually, equation of simple harmonic motion has this form. So the second derivative of x, the second derivative of x with respect to t plus omega square x equal to 0. This is usual form of simple harmonic equation, where omega is a cyclic frequency. So omega is equal to square root of cyclic frequency means 2 pi f. So omega is cyclic frequency, f is usual frequency. So the question is to find the period. It can be written 2 pi divided by period t. So t is period. Now let's look at this equation. Let's write this equation in this form. You can see that omega square is a. So if you write this equation in this form, we see that here it has a. If you move this term to the left hand side, it becomes plus. And comparing these two, you get that omega is equal to square root of a. And from these two equations, we get that period is equal to 2 pi divided by omega. From this last equation, we get t equal to 2 pi divided by omega. And omega is square root of a. Then we get 2 pi divided by square root of a. So this is the answer and the working formula. And a is 100. Let's calculate this. It's 2 pi, approximately 6.28. Let's write it approximately 6.28 divided by square root of 100 is 10. So it becomes 0.628 seconds. This is the answer. So answer is 0.628 seconds. Any questions? If no questions, you may think about it. You can look at the lectures, and if you will have some questions, you can write on our Telegram channel. Next question is number 8, the derivative of a unit vector. This topic concerns vectors. Vectors, unit vectors. vectors. So the derivative of a unit vector. What are unit vectors? You know, unit vectors are in Cartesian coordinates. They are I, j, k vectors. I vector or j vector or k vector. So in general, we can write unit vectors as u vector. So not only Cartesian, but in general, okay, in general, u. So the question is the derivative of unit vector. What is the derivative of unit vector? In order to find the derivative of unit vector, we use the property of unit vectors. This is dot product of two unit vectors of the two same unit vectors. The dot product of two same unit vectors should be equal to 1. For example, I to I, or j multiplied by j, or k multiplied by k is equal to 1. Because dot product, definition of dot product is dot product of two vectors A and B vectors is equal to modulus of A, modulus of B, and cosine of angle between them, cosine theta. Theta is angle between vectors A and B. This is definition of dot product. The magnitude of dot product. The magnitude, the modulus of dot product. So in our case, u has a magnitude 1. This u has a magnitude 1, and angle between them is 0 degrees. Cosine 0 is 1. That's why this dot product is 1. We use this property of unit vectors to find its derivative. Let's find derivative let's take derivative from this last equation. So let's take a derivative. For example, with respect to r, r is radius vector. Oh, we can take derivatives with respect to time. It doesn't matter. On the right hand side, we get 0 because this is number, and derivative from the number is 0. Now, let's use the formula of derivative of multiplication of two functions. So derivative of u with respect to t multiplied by u plus u derivative of u with respect to t. This is formula of derivative of multiplication of two functions is equal to 0. So you see that they are the same, and you can write that this addition is 2u vector du vector dt is equal to 0. And we can neglect these two because on the right hand side we have 0. We can neglect this u. And you see that we get multiplication of two vectors, unit vector u and a derivative of unit vector u. Their multiplication is 0. Multiplication here is dot product. Of course, dot product, because initially it was dot product here. Here is dot product. Here is dot product. Here is dot product. And what does this mean? Dot product is equal to 0. When dot product can be 0? Look at this formula. If A and B is not 0, in our case they are not 0, the dot product can be 0 only when the angle is 90 degrees, pi over 2 radians. So angle is 90 degree, right angle. Cosine of right angle is 0. That's why angle between these two vectors is 90 degrees. That means derivative of unit vector is perpendicular to the unit vector, perpendicular to itself. So is a vector orthogonal to the unit vector? Orthogonal means perpendicular. Angle between them is 90 degrees. The correct answer is the first. Okay, I'll send you this file at the end. You can check it by yourself. You can do it again. Please try to solve all these problems by yourself after the lecture, after the lesson. Next one is question number 9. This is about circular motion. This is also kinematics. What is angular speed? So angular speed does not depend on the radius r at which it is calculated. Angular speed is always tangent to the trajectory, is always constant, is constantly changes direction. So I'll explain you what is angular speed. So angular speed is omega is equal to change of angle d theta dt is the derivative of from angle with respect to time. This is angular speed. We have angular velocity, which is vector. Angular velocity is the same thing, except for it has a direction. And its direction is always perpendicular to the plane of the rotation. So it's normal to the plane of rotation. That's why we can write here the un, normal direction, unit vector in the normal direction. So difference is angular speed is a scalar, and angular velocity is a vector. So for imagine, I'll show you the picture of the angular velocity. Let's draw some picture to imagine the direction of the angular velocity. Imagine that the body rotates in the horizontal plane in the direction of clockwise, or counterclockwise. Usually counterclockwise direction is positive in physics. Let's say that the body rotates in this. Well, let's say the body rotates in this direction. It's a counterclockwise direction. Then its angular velocity has vector, this vector omega has direction upwards. So this is omega. This is omega, direction of omega vector. If direction of rotation is clockwise, then omega will be downwards, the opposite direction. Now let's come back to the question. We are talking about the angular speed. So the second one is not correct. It's not tangent to the trajectory. It's orthogonal to the trajectory. It's always constant. It's not constant because when you take derivative, so if, for example, theta depends on the square of t, omega depends on t. That's why it's not constant. And the constantly changes direction. No, it doesn't change the direction. Angular speed does not have direction. But if you talk about angular velocity, it doesn't change the direction. Does not depend on the radius r at which it is calculated. Of course, it doesn't depend on the radius r. It depends on how theta changes with time. Of course, you may ask, we have formula, the dependence of angular speed with linear speed, which is v equals to omega multiplied by r. So we have this formula, and you may ask, so if you find omega from this equation, it should be velocity depends on radius. Yes, this formula is correct, but it doesn't mean that omega depends on radius. Why? Because if you increase radius 2 times, velocity increases 2 times, and their ratio doesn't change. Imagine that, so we have a body with radius, some radius. Imagine that, how to explain this? So if something is rotating and it can change its radius. For example, if we have a rod, so if we have a rod which rotates around this axis, in the clockwise or counterclockwise, it doesn't matter, direction. Imagine that we have a body which can move along this rod. So connected, this body connected to the rod. So during the rotation, we can fix the radius. We can change the radius. For example, we fix initially radius 10 centimeters, and this body rotates with angular velocity omega, for example, 1 radians per second. Then we change the radius, for example, 2 times, increase 2 times. And you see, if r increases 2 times, now velocity becomes 2 times greater. So 2, these 2, and cancels out, 2 cancels out, and it doesn't depend on change on radius. That's why the correct answer is the first. Does not depend on the radius. Next question is number 10. The axis of a spinning top rotates around the vertical axis that passes through the point of contact with the ground. This is also rotational motion of a rigid body. Rigid body. So this is about the spinning top. Let me try to draw it. So if you have played during your childhood this kind of spinning object, it rotates around this axis, but this axis itself rotates around the vertical axis. The question is about that. So it has 2 axes of rotation. We have this axis of rotation and this axis itself rotates in the vertical axis. This axis of rotation. I will send you the video later about this on the Telegram channel. You will see if you didn't play it during your childhood with this kind of spinning object. And the question, why this happens? So the torque, so you should know what is torque here. The torque is tau, the torque is a vector, is equal to radius r vector so this is a cross product of radius of rotation. This is, we call this a lever arm, multiplied by force. And let's see what is a center of gravity. Let's note that it has a center of gravity here. It has a center of gravity here, for example. This is the center of gravity, and from this point we can put the gravity force. This is the gravity force or weight force. And try to find the torque of this force. So what is the direction of torque with respect to this point? So this is radius vector. So this is vector F, this is vector R. What is the direction of these two vectors? Cross product of these two vectors. In order to find the direction of cross product, we use right-hand rule. So R multiplied by F. So you put your hand you put your hand in that way. So your four fingers should rotate from R to F, and your thumb should be perpendicular to the plane of this figure. And the direction of torque becomes from us. So usually in physics, when you cannot draw in 3 dimension, usually we note it as follows. We draw a circle like this, and then we put X inside this circle. Or we put plus inside this circle. So we draw it like this. What does it mean? It means that the direction of torque is from us. So according to the right-hand rule, if R and F has direction. This is radius vector of this point. This is force. Torque has direction from us. That torque rotates this wheel or this top around this vertical axis. The answer is the first one. Next one is question number 11. An artificial satellite of mass m describes a circular orbit around the Earth. The Earth's mass is m. Calculate the rotation period of the satellite as a function of the radius r of the orbit. So this is now about the Newton's second law for the gravitational motion and rotational motion. Newton's second law for the motion, for the satellite motion. Now let's apply Newton's second law for satellite motion. F gravity equals m mass of the artificial satellite multiplied by centripetal acceleration. This is Newton's second law for the satellite. And gravitational force is gamma mass of the satellite, mass of the Earth divided by radius square. If you know the Newton's gravitational force, it has this form, where gamma is called gravitational constant, which is equal to 6.67 10 to the minus 11. Newtons meter square divided by kilogram square. So this is Newton's second law, gravitational force, mass, and acceleration is, centripetal acceleration is omega square multiplied by r, where omega is angular speed, angular velocity is equal to 2 pi divided by period t. Substituting this omega to here, we get the following equation. Omega square is 4 pi square divided by t square. And we can cancel out masses here. M and M can be cancelled out. And this r square, r can be written as r cubed here. R and r square becomes r cubed. And this t square can be moved to the left hand side. And gamma m can be moved to the right hand side. So, and then finally, in order to find t, we make a square root from both sides. This is final formula. And this 4 pi square can be moved outside of the square root. It becomes 2 pi. So for prettiness, let's move r cube to here. Then we get this equation. So 2 pi r cube gamma n. The answer is the first as usual. 2 pi r cube gamma n. Question number 13. The angular momentum of a system of particles is conserved. This is about the conservation of angular momentum for a system of particles. If the sum of external torques acting on all the particles is 0. So I'll explain this. Angular momentum is L. This is vector. And this equal to I omega. Omega is vector, you know. Or another form is this. The mass multiplied by radius vector cross product of radius vector and velocity. This is for a point particle. And if we have a system of particles, we have to the sum up. We have sum here. Sum from over all particles. All particles. So, and this should be conserved, should be constant. And you know that the torque, definition of torque, torque is also vector, is the derivative of angular momentum dl with respect to t. So this is definition of torque in terms of angular momentum. And if torque is equal to 0, then derivative of angular momentum is 0. When derivative of angular momentum is 0, when it's constant. So if you integrate this, you get L is constant. So angular momentum conserves if the torque is equal to 0. This is external torque. The sum of the external torques acting on all the particles is 0. So in case of system of particles, here should be the sum of all torques. So this is net torque, actually. This is net torque. The sum of all torques. Question number 2 is a homogeneous solid cylinder of length 40 centimeters, radius 2 centimeters, and a mass of 2 kilograms rotates in a horizontal plane around a vertical axis perpendicular to its axis in the middle point O as a result of an impulse J received perpendicular to an extreme. As a result of the friction, the cylinder stops after traveling a lap. Calculate initial angular speed, omega 0 of the cylinder, and the momentum m of the forces of friction. Let's draw a picture for you to imagine what's happening. So here we have a homogeneous cylinder. Let's imagine that this is a solid homogeneous cylinder of length 40 centimeters and radius 2 centimeters and mass 2 kilograms. It rotates in horizontal plane. So we have a vertical axis here. It rotates around this vertical axis in horizontal plane. It rotates like this. As a result of the, an impulse J received perpendicular to an extreme. So impulse J is received at an extreme, means at the end. So here impulse J received in this direction. This is an impulse. And what is impulse? You know that impulse J is a vector quantity is equal to integral f dt. Or if f is constant, it's equal to f delta t. This is impulse. Of course, f is a vector. And you know that we have impulse momentum relation. So impulse J equals to change in momentum. So this is called impulse momentum relation. Or in simple way, we can write that f delta t equals to delta mv. P final momentum minus initial momentum, P initial. This is called impulse momentum relation. So we can find the torque. The torque tau is equal to force F multiplied by L over 2. L is the length of this cylinder. Why L over 2? Because the total length is L and the lever arm is L over 2. Lever arm is the distance from where the force acts to the rotational axis. So this distance is L over 2. So torque is FL over 2. And we have the relation between torque and angular acceleration. So torque tau is equal to moment of inertia multiplied by angular acceleration, I alpha. Angular acceleration is a vector. And angular acceleration can be written in terms of angular velocities. Change in angular velocity divided by time. So this is torque, delta omega divided by delta t. From here we can find delta omega. So we put torque equal to FL over T Okay, let's put torque equal to FL over T here. And let's put, let's find delta omega from here, change in angular velocity. Delta omega is, from here is F delta T. So delta T moves to here. Delta T moves to here. I moves to here. I moves to the denominator. And F delta T is you see, is impulse J. So let's write it J L over 2I. So L is the length. Okay, let's write it small l, because capital L is angular momentum. Let's write it as small l. And if initially it was at rest, so delta omega is omega minus omega 0. If initial angular velocity is 0, then we can find in omega equals JL over 2I. So this is angular velocity after the impact of the impulse. So final angular velocity after the impact of this J. Now it starts to rotate. That means now this omega becomes initial angular velocity for the rotational motion of the cylinder. So actually this is initial angular velocity. This initial is when it was at rest. So that's why, in order, let's put right here at rest. And this is the answer for part A. Let's calculate it. J is 5 10 to the minus 2. Zero point zero 0.02, 0.0, yes, 0.05. L is 40 centimeters. Let's convert it to meters. It's 0.4 meters divided by 2. And what is moment of inertia of the cylinder passing through around the axis, passing through its rotation, center of rotation, around this axis? If I remember correctly, it was 1 over 12 mr square. Two and 1 over 12. Okay, let's check. Is it 1 over 12 or not? I forget. No, I think it's 1 over 6. 1 over 6. One over 12, I was correct. So this is the rod, this is the axis, and passing through the center is 1 over 12 ml square. This is 1 over 12. Then it becomes 1 over 6, canceling with these two. So this is 1 over 6. 6 goes up. 6 goes up. And here we get ml square. We can cancel this L here with L here. So we get here L. This L cancels out. Here we have ml. M is mass is 2 kilograms. 2 multiplied by L, length 40 centimeters. So then we get 3 here, 3, 0.15 divided by 0.4. 0.375 radians per second. Okay, this is the answer for the first part. Actually, this is 0.375. 0.37. Okay, it's correct. Now calculate this moment of M of the forces of friction. So we know that the cylinder stops after traveling a lap. So it has one rotation, one total rotation, and it stops. What does it mean, one total rotation? One total rotation means that angle of rotation, theta, the total angle of rotation is equal to 2 pi, because one total rotation is equal to 2 pi. And again, we can use equation for rotational dynamics. Equation for rotational dynamics is torque. So actually, I noted the torque with letter tau, but here it suggests to note the torque with letter M. M is the moment M. Actually, it's the torque, the friction force. Okay, let's note it as M. M equals to I multiplied by alpha. Now it's alpha 2, because this alpha was the acceleration when during the impact of the impulse. But now alpha 2 is deceleration under the friction forces. So we can find acceleration alpha 2 is m divided by I. Then we can write that the kinematic of rotational motion, the theta is equal to, so let's write it like this, omega is equal to d theta divided by dt. So when you integrate this formula, you get theta equals integral omega dt. Alpha 2 is d omega dt. When you integrate this, you get omega minus omega 0 equals alpha 2 t. And from here we can find omega. And we can substitute this omega to here and integrate it like this. After the integration, we get omega 0 t plus alpha t square over 2. You knew this equation before. I just showed how to prove it, but during the test you can use directly this formula. And what is given is time t is not given here, so we know theta is 2 pi. Total angle is 2 pi. We know initial velocity. We just found the initial velocity is 0.375. And we know alpha 2. Alpha 2 is m divided by I. We can solve this quadratic equation and find time t. But another way, we have the alternative way. Without using time t. We can use theta equals omega average multiplied by omega square minus omega 0 square divided by two alpha 2. You can use this formula. Let's find alpha 2 from here. So it says that at the end it stops due to the friction. That's why the final angular speed is 0, omega square is 0. And you see it's negative. Yes, when deceleration it will be negative. So from here you can find alpha 2, and then finally moment m can be found from here. So moment m is equal to minus I omega 0 square over 2 divided by theta. So this is this is the final result, final formula. So this is minus I is calculated here, 1 over 12 ml square (1 over 12 ml square), and this becomes 24 theta. Theta is 2 pi, you remember. Let's put 2 pi. 48 pi. And this is final formula, where omega 0 is calculated here. So m is mass, m is small m, is mass. Here also m is mass, small m. So m is 2 kilograms. L is 0.4. This should be squared. Omega 0 is, we just calculated, omega 0 is 0.375. And 48 pi is 3.14. Let's calculate this. It becomes 2 multiplied by 0.4 multiplied by 0.4 multiplied by 0.375, 0.375 divided by 48 divided by 3.14. Approximately 3 10 to the minus 4. Minus 3 10 to the minus 4 newtons meter. So 3 10 to the minus 4, let's check. Yes, it's about 3 10 to the minus 4. I approximated, it was 2.98, 2.9, approximately 2.9. So this here we use dynamics, but this kind of problems can be solved by using energy conservation. So you can write the energy conservation. The second way to solve this problem is to write energy or work energy theorem. You know that work done by the friction is moment of the friction multiplied by uh, the distance. Angular distance is angular displacement theta. This is work done by the friction forces. These friction forces stop the cylinder from rotating. That means the cylinder initially it had kinetic energy I omega square over 2. So work done by the friction is equal to the change in energy. Energy changes from this value to 0. From here you can find directly the torque M. So torque M is, you move theta to here, then I omega squared divided by 2 theta, and I is 1 over 12 ml square, and you get again this formula. You get again ml square. This is actually omega 0 square divided by, then this becomes 24, and theta is 2 pi, it becomes 48 pi. So this way is more simpler, I think. But in order to explain everything for your understanding, I explained all the 2 by 2 methods. Okay, and the last two quick questions on mechanics are the question about the conservative force. When a force is conservative, you can look at the lectures, and there it's explained that if the gradient of the force is equal to 0, or if the nabla, we have a nabla operation, nabla times f vector, if this equal to 0, then the force is conservative. Look at the lectures, you can find this explanation of this. The answer is this. Actually, this is not x, this is cross product of, actually this is rotor f. You know from algebra, this is rotor f. From the field theory. And the last question for today is, the force is given where A and B are constants of suitable size. Is it conservative? Let's check how to check the force is conservative or not. One way is to use this formula, rotor F equal to 0. Another way is is partial derivative of fx with respect to y partial derivative with respect to y should be equal to partial derivative of fy with respect to x. So if this equation satisfies, then the force F is conservative. So what is Fx? X component of the force is given here is equal to A multiplied by Y, AY. And Y component of the force Fy is given here. It's minus bx. Let's take derivative, y derivative from fx. Y derivative from fx is, okay, let's write them here, here. So take a derivative with respect to y from here. It becomes a. Actually, here it should be minus. No, minus comes from here. So x derivative from fy is minus b. So answer is a should be equal to minus b. So just when a equal to minus b, this becomes conservative force. So that's all for today. If you have some questions, please write them on the Telegram channel. I'll try to answer them. See you next time. Thank you for your attention. I will upload this video record of this lecture, this lesson, after the editing, video editing, and decreasing file size. Thank you for your attention. See you next time.